Okay, here we go with a look at what happens when you take a wire with the current running through it and you bend the wire into a coil shape. The word for a coil is solenoid. That's how we describe that shape. So by a coil, what I mean is a wire that is going around like this, kind of bent into a coily shape. It's actually kind of difficult to draw these coils on a board like this. You could do it like this, but it's difficult to see it in 3D. So sometimes what I like to do is I like to put a bar in the middle just as a reference point. You don't necessarily need to have a bar in the middle, although there are reasons why we might do that. And then you can have your wire kind of going up like this and around. So this is the kind of way I like to draw a coil of wire, because you can kind of see the 3D part of it. And you have to be careful. You have to notice that on one side over here, the wire is coming up behind the bar and wrapping around the front. So every time it disappears behind the bar, you can kind of see it. And then on this side, you'll notice that it's coming down in front of the bar. So that kind of gives you an idea of a coil. We can also just have a quick look on the internet, and that could give us an idea of some pictures, just for a visual. So here I've pulled up some solenoids, and we can see this one right here that I'm circling with green is a pretty good example of a coiled wire. Don't worry about all these fancy pictures underneath. We'll get to those later. So this coiled wire is what we're going to look at. Okay, good. So let's go back to our picture here. We're going to look at a solenoid. Well, first of all, let's remind ourselves when we have let's say we have a wire that's going like this, and current is flowing through the wire. Perhaps the current is flowing in this direction, the conventional current, which we describe as positive charge flow. So this is the positive end and the negative end of the wire. And remember, we have our right hand rule number 1, which comes from Oersted's principle, which tells us if we grasp this wire, let me take a green color here, and we sort of draw our hand. So our thumb is pointing this way, and our hand comes up, and it grasps the wire, our little fingers like this, little fingernails, and we grasp the wire with our fingers, and our hand is sort of, it's like this. So those little fingers are sort of like wrapped around in front, kind of pointing towards you. Right? And we can say that that's the direction of the magnetic field. So it comes sort of around the back. It goes around the back like this, following the fingers, up and around the front. So if you imagine that in 3D, that's how the field is sort of situated, the magnetic field around the wire. And of course, it extends outward, and it goes all along the wire everywhere, right? Okay, so now what's going to happen is we're going to twist the wire into a coil and see what happens. So what I'll do is I'll start by just drawing one coil. So here's my wire. I'll wrap it around like this, and I'll give the wire some thickness like this, and it's going to go sort of in behind there and come out the other side like that. So there's one twist or one coil of the wire. Now what I'm going to try and do is I'm going to try and draw my right hand on this wire. Okay, let's assume that the current is going this way. So my thumb is pointing this way, and my fingers are wrapped like this. There's my fingers with their little fingernails sticking out and some knuckles here, right? And so that's the way my hand is wrapped around the wire. So you can see my little fingers are pointing, sort of sticking out towards us in the middle of the coil as the current goes around. I'll go back here and just add a plus and a minus to show the current is going in the direction that my thumb is pointing. Well, now if you think about this, that means that in the middle of the coil, the magnetic field is sort of coming out of the board towards you, out of the screen towards you. And then it wraps around, and on the outside of the coil, it goes back into the screen. So we could draw that sort of, something like this, going behind, and around like this. And we would say that it comes out from behind and goes around this way. That's kind of the direction that it's going. That's our right-hand rule. Now, if I slide my right hand around the wire, what's interesting is if I slide it up to the top, then my thumb is pointing this way. Oh, we have a little problem. There's my thumb, okay. Pointing this way, and my fingers are now sort of upside down. And my hand is doing this. So you can see how I've just slid my hand around the wire to the top. Because my thumb hasn't changed its direction, the electricity swings around the curve, and you'll notice that my fingers are still pointing in towards me in the middle of the coil. And if I slide my hand all the way around so that my thumb is pointing way over here, we can see my little fingers on this side, sort of the same idea. My hand is still grasping the wire in the same way. And so what we notice is that the fingers in this middle region here of the coil, the fingers are all pointing out towards us. Sometimes when we want to show pointing towards us, we use a dot. Remember, I think we may have talked about that. When you're trying to show the directions of coils or magnetic fields, and you want to show in and out, you can show an X, which means into the screen, like the tail feathers of an arrow as it shoots away from you. And a dot out of the screen, which means coming towards you. That's the tip of the arrowhead as it's shooting out towards you. So in the middle, we have shooting out towards us. And then all around the outside is where the field is going away from us, like this. So you could imagine the field lines kind of coming around like, and then shooting back out again. I guess every one of these could be drawn, like that. And it gets complicated, but it's easier just to imagine in the middle of the coil, all of the magnetic field is coming towards us. Now, if I just turn the picture a little sideways, so the coil is kind of on a sideways slant, that means that all of the magnetic field is going this way and shooting out through the middle of the coil, so sort of to the side. And then we can imagine a coil of wire that's coiled like this with multiple coils. Well, now you're just repeating the same idea. And so what that means is that the magnetic field is shooting through the middle of the coil, like that, all the way through. It's just adding up. And so what we get in the middle of the coil is a very strong magnetic field moving through the middle in a particular direction. And of course, what we want to do is we want to be able to determine what that direction would be, and we want to use a right-hand rule to figure it out. So once we understand that the magnetic field moves all in the same direction through the middle of the coil, what we can then do is we can make up our rule. So let me draw a coil. I'll put the bar in the middle to give us a little bit of extra visual. And I'll make the current, the wire blue, wrapping like this around. So there's my wire. And sometimes what we do for these coils is we just put a little symbol here. Remember your electrical symbol of a cell to show the negative and positive direction. So that means that we're always talking about conventional current, which is the charge, positive charge flow. So it means that the current is going this way. And it's going up right here on the front side, but it's going down on the back side. And then it comes around and goes up on the front, down on the back. So all of the front wires that are facing or closer to us have the electricity going up, whereas down below, or down behind, I mean, they're all going down. So there's my little arrows to show which way the current is going. Now, what I want to do is I want to figure out, we know that the magnetic field inside this coil is going through the middle of the coil, but we don't really know if it's going this way or if it's going this way. There's two different ways it could go. We know it's going to go one of those two ways. So what we do is we take our right hand, and this time we kind of reverse the meaning of our fingers and our thumb. So for right hand rule number 1, I'm going to remind you that with right hand rule number 1, we used fingers to show the direction of the magnetic field, right? And we use thumb to show the direction of the current. And that's conventional current, plus to minus. That's important to remember. Well, right hand rule number 2 is for a coil or a solenoid. This one is for a straight wire that's not twisted all up like this. So for this one, what we're going to do is we're going to swap. Our fingers are going to show us the current direction. And again, plus to minus conventional current. And our thumb is going to now show us the magnetic field direction. So we've kind of flipped the meaning of the two things. So now we have to draw our hand on here and try to figure it out. So what we're going to do is we're going to take our right hand and we're going to get our fingers to wrap around in the same direction as the coil of wire, but showing the direction of the current. So remember how I said that the current along the front part is all going upwards. You see the little blue arrows right in the middle of the black box, which means if I want to grab this, my fingers have to point up on the front side and curl around the back. So my fingers have to sort of curl around, right? Kind of something like this, around the back. These are my fingers curling around the back. 4, right? And then my thumb is going to sort of, my hand is actually going to come down here. I'll draw the fingers a little further down, little knuckles. And then this is the palm of my hand. And then my thumb is going to stick out this way, right? Hard for you to see that, so maybe I can shade it in to give you a little better view. Let me get a little crayon here and pick this green and just kind of shade it in. So here's my hand over the top. See, this part is all out in front. And you can't see the tips of my fingers because they're sort of down behind. So you see how my fingers are lined up along with the blue arrows, the way the current is going. And my thumb then is pointing over here. Now, what does that mean? Does that mean that the magnetic field is going this way? Or does it mean that it's going the other way? Right? Is it maybe this one? What does it mean? Well, the problem with magnetic fields is they go in circles, so it's difficult to figure out the direction. What this essentially means is that the magnetic field lines will form what's called a north pole at this point and a south pole at this point. And what that would look like, if I draw, I'll just get another color here and make the picture even better. The magnetic field lines then would run from the north to the south pole, and then they would run through the coil in this direction. So you see how your thumb is pointing that way, at least for the inside, right? Your thumb is pointing in the direction of the magnetic field lines inside the coil, because see up on the top here, they're going the other way. But we have to think about inside the coil, not outside. And of course, they would also go in this other direction around like this. So there's how we get the magnetic field lines. And of course, a coil like this, as you can see, forms the very same magnetic field as a bar magnet. Remember, when we drew bar magnets, when we first learned about magnetism, we drew the magnetic field lines around them, right? In this same way. They kind of went out like this, like that. And that's what they're trying to show on this picture now. You can see how, I go back to some of these pictures. Let's pick, this one looks very similar to the one that we just did. So let me grab my pointer so I can actually see if I can blow this picture up. No, there we go. So we can see it here now, and now I can put some color on here. So let's go back, get a nice red pen, and we'll have a look at this one on the right-hand side with the purple and brown. It looks very much like ours. You can see inside the coil, right? If you were to try and grab this, right, you would grab your hand, and your hand would sort of grab around this way. There's my knuckles. There's the palm of my hand, and my thumb is sort of pointed out here. That's the kind of way, and the coil would be in here like this. And so you can see the magnetic field going here through, and your thumb is pointing to where the North Pole is on the magnet. And this does make a magnet. That's what's interesting. It makes an electromagnet, electromagnetic field inside of a coil. And it's a cool kind of magnet because it only works when the electricity is flowing. You can use a switch and turn it on and off. So it's a magnet with a switch. And we'll talk about that in a second. All right. So that's the basic idea. Right-hand rule number 2 says that your fingers point in the direction of the current. The fingers now curl around the coil the way the electricity is flowing, and your thumb points to where the North Pole would be. So we could do one more example. Let's just take a coil this way, and let's draw our little wire going, oops, that didn't work. Let me go back. Let's draw that like this. So I've reversed the picture. We'll keep our current the same. So here's my negative and my plus. But now what you'll notice is that when you look at which way the current is going, it starts at the plus and it goes this way. But look, it's now going up behind, as opposed to this picture right here where it went up in front. So I've got it backwards now. So it's going up behind, and now it's coming down in the front. All the fronts are coming down, and all the backs are going up. That's the direction of the current. So now when I draw my hand, instead of drawing it the way I drew it here, where you can see the back of my hand, you actually have to grab around behind, so that this time what you see looks more like this. Your hand is twisted, so in front you actually see your fingers now. So here come my fingers. There's my fingernails. Finger, 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 finger. Okay? And my knuckles on the top here. And my hand is reaching around the back like this. And my thumb is now sticking out this way. And I'll grab my crayon and shade it in here on the top to give you some perspective. This part is all sort of in front. My hand. So you see the hand is reversed, right? I know my artistic skills are not that good, but there's the two hands. One with the back of the hand facing you on top. Now the palm is facing you. You can see the little fingertips. And you notice when you do that, your thumb points the other way, which means that for this coil, we can determine that the magnetic field would have a north pole here and a south pole here. And now the magnetic field would flow this way in the direction of the thumb inside the coil. And then it would loop around, and just like before, and it would form the same magnetic field as the bar magnet. And so the electromagnet is a device that we can create, electromagnet. It's kind of a misnomer because all magnets are in a way electromagnetic, but this specifically refers to magnets that are made by using coils of wire. And so, you know, we take an object like this and we put the wire, wrap it all around there. Nice, nice, nice. And this time we put our power source in here, but we also put a switch. So now, when I close the switch, electricity flows. And when electricity flows, it makes the coil a magnet. It causes Oersted's principle, moving charge. I use my right-hand rule. This is the same coil as the one I just drew up here, so it's the same idea. We have a north pole here and a south pole there. And that would turn this coil into a magnet. And then, of course, if we open the switch, like I have it drawn now, that would shut off the electricity, which makes the magnetic properties also disappear. Now, you can make a magnet like this just with a coil of wire, nothing inside but air. But air is not the best thing for magnetic field lines to form in. Air has not a very high, what we call magnetic permeability. It's better to use a substance that the magnetic fields can more easily be set up in. So typically what we do is we do put a bar inside the coil. And usually it's a bar of iron because iron is very magnetic. And so we put a bar of iron inside there, and that makes the magnetic field even stronger. And so it makes for a far more effective magnet. And essentially now we have a magnet on a switch. So, you know, you can imagine if you're trying to move a giant bunch of cars, big heavy cars in a scrapyard. So you have this big crane that has a big magnet attached to it. Big crane, right? That's my crane. And you lower the magnet down, you turn on the switch, here's the switch, you flip the switch, and now suddenly the giant coils of wire inside this has usually got a big core of iron with wire coiled around it. Now it becomes a magnet and the car sticks, and now you can hold the car and lift it up and move it somewhere, and then you just turn off the switch and the car can be dropped. It's an electromagnet. Electromagnets like this are very commonly used in circuits to turn a circuit on or off. They make like a switch. So I could show you an electromagnetic switch. Let's draw, let's see. What we would have is we would have a little bar, and this bar would have a little coil of wire around it. Let's go back and fix that. Like that. And this coil of wire would be attached to a small circuit with a small power source. Now, this blue circuit is not connected to the main circuit. So what I have now is I connect the main circuit like this. And then maybe this main circuit has a very large power source. And we don't want to touch it. You don't want to touch it with your fingers. You don't want to be risking a major shock if you were to flip the switch or put a key in, for instance, a metal key to turn on this particular circuit. So what you do is you have a little piece over here that's made of metal, a little metal block with a spring on here that's metal, so it's part of the circuit. Now, maybe this circuit runs a very powerful motor. Maybe it runs the starter motor of your car. The starter motor of your car delivers like about 400 amps, and it's very dangerous. It can kill you very easily. So you don't want to be messing with it. So you'll notice the blue circuit is just a little baby circuit with a very small voltage, very safe. And that's where you would have your switch. I should have put the switch in there. Maybe this is where you put the key in the slot, right? There's your key. Or it's in any kind of switch. So when you put in the key and turn it and activate the switch, this little bit of current can flow in the blue circuit, which makes this little coil at the bottom a magnet. And that magnet will pull on the little metal piece on a spring. It'll pull it over so that it will come over here and attach. And once it attaches, now the current that's in the big circuit can flow because it's attached. It's all metal pieces connecting in there. And the motor over here can run. But you didn't have to touch the red circuit with your key or your fingers or anything, right? And when you turn the key off, the magnet stops and the little spring here springs back. And what it does is it pulls this back so it's not touching anymore, and that shuts off the electricity, and the motor then shuts off and stops running. Now, this is not the engine. This is the starter motor of your car, right? So, but it's the part that goes right at the beginning when you turn the key. This motor turns over the engine. Once the engine is rolling or moving, the gasoline is what powers it. But this is how we just get it started, right? Just to start. So it only has to operate for a second. So you turn the key for a second, this connects, and then the key snaps back a little bit, and the connection disappears. But now the car is already rolling, and the gasoline is now flowing, and the spark plugs are pushing the pistons, and it does its thing. So this is called a solenoid switch. This thing that I've drawn with the magnet is called a solenoid switch. And you might hear that sometimes. These things can wear out. And so you might go to the garage one day with your car and they'll say, oh, your solenoid is gone. So what that means is there's a little switch-like circuit like this. And these little bits and pieces that are moving, they wear out over time and they have to be replaced. So that's a good application of Oersted's principle, making an electromagnet when we coil the wire around. And of course, now we have right-hand rule number 2 to help us determine the directions of magnetic fields with coils of wire or solenoids. So I think that ends our little discussion for today.